Chapter 8 of the Abstract Algebra series is Introduction to Groups. And problem number 1 says that we need to show that 5z, which consists of the set of all numbers that can be expressed as 5 times an integer, we need to show that that group under addition, that set under addition is a group. So all that we're really given is that we have a set. And we have to check 4 properties to determine whether that set is a group. To show that a set together with a binary operation star is a group, we have to show that 4 properties are satisfied. Number 1, we have to show that the set is closed under the binary operation. And in this case, the binary operation is addition. We have to show that the binary operation is associative. We need to show that the set contains an identity element. And then finally, we have to show that each element in the set has an inverse that is also in the set. So let's start with number 1, closure. We know that the set 5z contains all multiples of 5. If we randomly choose 2 elements from this set, let's say that those elements are arbitrary and they're x and y, where both of those numbers are a multiple of 5. Why do they have to be multiples of 5? Because we are drawing, or we're selecting elements from 5z, which means they have to be multiples of 5. If we add together 2 multiples of 5, we get a result that is also a multiple of 5. For example, if we let x equal 5 times p and y equal 5 times q, where p and q are integers, if we add those together, then x plus y is 5p plus 5q. And that gives us 5 times the quantity p plus q. And if we add p and q, what do we get? We get another integer. So x plus y, the sum of these 2 arbitrary elements, is just another multiple of 5. And therefore, we have closure. So the first property is satisfied. Now for number 2, associativity. All elements in 5z are integers, and under addition, the group of integers is associative, so we would say that 5z inherits associativity. Number 3, we need to show that the identity exists inside the set. In other words, we need to show that there exists an element e in 5z such that e plus p is equal to p, and p plus e is equal to p, where e and p are in the set. Since 0 can be represented as 5 times an integer, the integer being 0, then we know that 0 is in the set. And if you add p to 0 from either the left or from the right, the result is still p. So we have found the identity element in 5z, and that identity element is 0. And finally, we will check to ensure that each element in the set has an inverse. This means that we need to show that for any p that we choose in 5z, that there is an element q in 5z so that the sum of p and q is 0, which is the identity element. So let's let p equal 5n and q equal to 5 times negative n, which is negative 5n. The sum of p and q would be 0, which is the identity element. Therefore, any arbitrary element in 5z has an inverse. Therefore, we have satisfied the 4 properties. Therefore, 5z does constitute a group. Problem number 2. Problem number 2 says, suppose that G is a group. This differs from problem number 1. In problem number 1, we were given a set. We had to prove that that set was a group. But now we're given that G is a group, and we see that if we multiply these elements in G, we get the identity in G. In other words, A times B times X times C times D is equal to the identity. And I'm referring to multiplication. That is sort of a generic rule in abstract algebra unless told otherwise. So how do we solve for X? Well, if G is a group, then we know that left and right inverses exist. So we just do the algebra. So given A, B, X, C, D is equal to E, the first thing I did was I took A inverse on the left side and on the right side. So multiply on the left by A inverse on the left side of the equal sign, which means I have to do the same thing on the left side. And of course, A inverse times A, that just cancels out, leaving me BXCD is equal to A inverse times the identity E. In the next step, I wanted to get rid of this B on the left side, so I just multiplied on both sides on the left by B inverse. And B inverse times B, that's a cancellation, leaving me X times C times D is equal to B inverse, A inverse times the identity E. The first two steps got rid of the noise on the left side of the X, and now I need to get rid of the noise that's on the right side, which means I will have to be multiplying by right inverses. And we will start with D inverse, working with the outer right part. So if I multiply on the left and right side of the equation by D inverse on the right, then XC is equal to B inverse, A inverse, E, D inverse. And finally, I need to get rid of this C, and since it's located on the right side, then I will multiply on both sides on the right side by C inverse. And then, of course, the identity multiplied by any element is just that element. Our final analysis is that X is equal to B inverse, A inverse, D inverse, C inverse. Problem number 3. Suppose H is a subset of Z and H is a group under addition. Okay, so H is a subset of Z, and we know that H is a group under addition. What does that tell us? Well, Z is the set of all integers, which means that H is a set of all integers, and H, more specifically, is a group, which means it meets the 4 properties from problem number 1. And our operation is addition. The question is H complement also a group under addition? Well, the answer is no, because if H is a group, then H must contain the identity in Z, and the identity is 0. So we know that 0 is an element in H. But H complement contains all of the elements that are not in H. In other words, H complement does not contain 0. 0 is not contained in H complement. Well, that means that H complement lacks the identity element, and therefore H complement is not a group. Number 4, disprove that a squared is equal to b squared would imply that a is equal to b. Well, if we look at the Klein 4 structure, Klein 4 being a group, it's a special group because the identity appears on the diagonal, in each position along the diagonal, which means that each element is its own inverse. In other words, A star A, or A times A squared, is E. But that also means that B squared is E. So B star B, or B squared, is the identity E. Which means we have shown that A squared and B squared are both E, which means A squared and B squared are equal to one another. But as we can see, A and B are distinct elements. They're not equal to one another. So that would prove that just because A squared is equal to B squared in a group, that does not necessarily mean that A is equal to B. So this is a proof by counterexample. Number 5, are the odd integers under addition a group? Explain. Well, since the sum of two odd integers is an even integer, then this set under addition is not closed. Therefore, the set of odd integers under addition is not a group. In order to have closure, you would have to add two odd integers together, and the result would be another odd integer. Problem number 6 says to show that if A squared is equal to E, where E is the identity, for all elements A in a group, then the group is commutative. We start by choosing two arbitrary elements in the group. So let's choose A and B. Since we have a group, we know we have closure, which means that A star B has to be an element in the group. And if A star B is an element in the group, then they have to satisfy this property. In other words, A star B times A star B, which is A star B squared, would have to equal E, because all elements in the group meet that criteria. Also, due to closure, we know that B star A is an element in the group. If A star B and B star A are elements in the group, then also due to closure, A star B star A should be in the group. Since all groups have associativity, I can remove the parentheses here, and that would give us this look. And remember that B star B would have to equal E. And finally, the remaining A's, if they operate together, you get A squared, which is equal to E. That gives us this fact. A star B, which is equal to E, is equal to A star B star A. And since we have a group, we know that the left cancellation law holds, which means that A star B is equal to B star A due to the cancellation on the left side. Therefore, the group is commutative for any arbitrary elements A and B in the group. Number 7, show that in a finite group, the number of elements X such that X squared is equal to E is even. Okay. We know that the group G contains the identity, and the identity squared would be equal to E. So this is one element in the group. But consider the group of elements such that x squared is equal to e, where x is not the identity element. Let's call this set of elements H. So all of the elements in H satisfy the property that if you take each element and square it, you get the identity. Well, this has to be a finite group of an order that is either even or odd. All of the other elements A are paired with a unique inverse, A inverse, which requires an even number of elements. So let's call that group I. So what do we have? Well, I have G, which has an order to it. And I've now partitioned G into three parts. We have the identity that's in G, and its order is 1. And then I have H, which consists of all elements such that their squares give you E. And at this point, I really don't know the order of H. So I'm going to suspend that for now. But I do know that the order for I, since I contains the remaining elements, and each element A in I has to be paired with an inverse, A inverse. So that means that the order for I has to be even because of the pairing. So what does that mean at this point? Well, suppose that the order for G is odd. G has an odd order. Well, if I is even, and we know that the order on the front end, the set that contains the identity, that has an order of 1. And if you add an even and an odd, you get an odd. And if you add an even here, you would get an odd. Since the sum of the first and last terms on the right-hand side is odd, then the order of H has to be even. What if the order of G is even? Well, if the order of G is even, then we could use the same logic to show that the order of H would have to be odd.